Welcome back. In this video lecture, we will talk about three-stage compression with water intercooling. Okay, so let's move on to the schematic and the corresponding pH diagram. This is going to be very simple. Why? Because I'm going to have three water intercoolers here, but the mass flow rate remains the same. The mass flow rate that flows through the low pressure compressor, intermediate compressor, and the high pressure compressor, as well as the water coolers, all are going to be the same. Okay, so it is in the evaporator that the heat is extracted. Okay, so that is your heat absorption from the region or space which needs to be cooled. Okay, so the mass flow rate is going to be constant. So the refrigerant flows through the low pressure compressor. It is cooled in the intercooler where de-superheating takes place, and at the end of the de-superheating, so if you look at the pH chart here, so 1 2, that is going to be isentropic compression. You travel along the constant entropy line. S1 is equal to constant, and 2 3 is your intercooling, and at the end of intercooling, the refrigerant is in the dry saturated state. So that is the result of using a water intercooler. Then it enters the intermediate compressor, and in that compressor again you have the compression which is isentropic, so S3 is equal to constant, and then you have the second intercooler where your de-superheating takes place again, and so point number 5 lies on the saturated vapor line. Okay, and then you go through the high pressure compressor. So there is again another isentropic compression which is along the constant entropy line, S5 equal to constant. And so in the condenser you have 6 to 7, and so point number 7, it lies on the um, so this is supposed to be a straight line, so let me draw it from here. So 6 7, so 7 lies on the saturated liquid line, and at the end of the condenser you have the refrigerant liquid, and that is taken to the expansion valve to reduce its pressure. And so you have 7 8, which is an isenthalpic process or a throttling process where H7 is equal to H8, and then 8 1 is where you extract heat from the region or space which needs to be cooled. Okay, so this is quite simple. There is no change in the mass flow rate. In all the components, you have the same mass of the refrigerant that flows through the system. Okay, so let's look at a sample problem and see how we can solve this. Okay, so here you have a vapor compression refrigeration system with ammonia as the refrigerant. It operates between the overall pressure limits of 2 bar and 12 bar. So which means the pressure of the evaporator is 2 bar. The pressure of the high pressure compressor, okay, which happens to be the condenser, that is going to be 12 bar. And then you have the vapors leaving the water intercoolers at pressure 4 bar and 8 bar. Okay, so you have at the end of the low pressure compressor, that is going to be your 4 bar. So let's say PI1, that is 4 bar. And then you have the intermediate compressor where your pressure is raised to 8 bar. Okay, and they have said the refrigeration effect. The refrigeration effect is given as 10 ton of refrigeration. So either you say it is 10 into 3.5 kilowatt, which is 35 kilowatt, or if you want to write it in kilojoule per minute, 1 ton of refrigeration is 210 kilojoules per minute. So it's going to be 2100 kilojoule per minute. Okay, and they want us to find the COP of the system, and they want us to find if the vapor compression refrigeration system operates without the water intercoolers. Okay, so let's go to the pH chart. So we have 2 4 8 and 12. Those are the pressure levels. Okay, So 2, 4, 8, and 12. So let's use the red color over here. So this is going to be my evaporator pressure PE P4, 4 bar. So that is going to be my PI1. 8 bar, that is going to be my PI2, and 12, let's take over here, that is going to be my condenser pressure PC. Okay, so these are the 4 pressure levels that we are going to look at. So if you travel across the 2 bar line and fix your point on the saturated vapor line, so that is going to be my condition number 1. So what I should do, I should travel across the constant entropy line. I have to travel across the constant entropy line, which should be parallel to these blue color lines that are shown here. S equal to 6 and x equal to 5.75. So I have a line intermediate between these two. Okay, so that's how I'm able to draw it over here. So then you have to fix point number 2 on the 4 bar pressure line. So this is my point number 2 over here. Then it passes through the water intercooler. So fix point number 3 on the saturated vapor line. Then once again, I have to travel along the constant entropy line, which is S3 equal to constant. So let's say this line over here, and I have to once again fix my point on the 8 bar pressure line. So you have 10, 9, and 8. So this guy over here, oh, I'm sorry. This guy over here, that is your 4. So let me erase this point over here. This is point number 4. Then I have a straight line on the saturated vapor line, so that's going to be 5. Then once again, I have to travel along the constant entropy line, which is S5 equal to constant. Drawing the entropy lines is the challenge for me over here. Okay, and I have to fix it on 12 bar. So let's say this guy over here. So this is 6. And I have to just draw a line, a 12 bar line, a straight line. Let's say this. It is supposed to be, oh, that's very low. So this is my 12 bar line over here. So this is 30 over here. So this is where we have 30. So let's join these two. Okay, so the 30 over here, this is my point number 7. Okay, and then from here I have to draw a perpendicular till I reach the 2 bar line. So this is my point number 8. So this H7 is equal to H8, which is an isenthalpic process, and then draw a straight line till you reach 1. Okay, so this 1, 2, 3, 4, 5, 6, 7, 8. So this is my the cycle which can be seen in the pH chart. So if we can fix the values or note down the values, so let me note it down on the next page. So let me change the color here. Let me use dark blue. So drop a perpendicular from 1. So you have 1400 line here and 1500 line here. So this is closer to 1400 and a little bit oriented towards 1400. So let's say H1 is 1420 kilojoule per kilogram. Okay, and then point number 2, if I drop a perpendicular, So it's closer to 1500 again. Let's say 1520. So maybe this guy is 1430 then. 1520 kilojoule per kilogram. And then I have point number 3, and this guy could be 1450. I'm pretty sure when you guys use the pH chart, you will be able to get much more exact values than what I am getting here. So H4, this is somewhere closer to 2 but lesser than 2. So let's say 1515 kilojoule per kilogram. Okay, and phi is closer to 3 but a little bit greater than 3. So let's say 1455 kilojoule per kilogram. And 6 is again a little bit lesser than H4. Let's say 1510 kilojoule per kilogram. Okay, and H7 equal to H8, that is closer to 300. So let's say 380 kilojoule per kilogram. So now we have noted down all the enthalpy values. So now all we have to find out is the refrigeration effect, the work done, and then calculate the COP. So if we calculate the refrigeration effect, that is going to be H1 minus H8. So 1430 minus 380. 1430 minus 380. Let me use the calculator. 1430 minus 380, that is 1050. Okay, so this is 1050 kilojoule per kilogram. And we already have the refrigeration effect as 10 ton of refrigeration, which is 35 kilowatt, which is kilojoule per second. So the mass flow rate is 35 kilojoule per second divided by 1050 kilojoule per kilogram. So this would give me the mass flow rate in kilogram per second. So I have 35 divided by 1050, which is 0.033 kilogram per second, multiply it with 60, you would get 1.98 kilogram per minute. So if you want it in kilogram per minute, you can multiply it with 60, or you can simply retain it with 0.033. Now there are 3 compressors here. So the low pressure compressor, it operates between 1 2, so it is H2 minus H1. So H2 minus H1 is 1520 minus 1430, which is simply, I think, 90 kilojoule per kilogram. Then the intermediate compressor, so that is H4 minus H3. H4 is 1515 minus 1450. So let's see what that is. 1515 minus 1450, that is 65 kilojoule per kilogram. And for the high pressure compressor, that's going to be H6 minus H5. So that is 1510 minus 1455. 1510 minus 1455 is 55. So total work done is WL plus WI plus WH, which is 90 plus 65 plus 55. How much is that? 55 plus 65 plus 90. That's 210. So you can multiply this with the mass flow rate and get the power, but for COP, I'm not going to do that. If you want, you can do that. So that is refrigeration effect divided by the total work. So this guy over here is 1050 and the net work is 210. So 1050 divided by 210 is 5. So that is the COP of the vapor compression refrigeration system when I use 3 water intercoolers. Okay, but the question is, in case if I am using with no water intercoolers are used, what happens? So let's say, let me use this black color then. So which means I have to travel along this constant entropy line over here till I reach the 12 bar pressure line. So that intersects here. So this is going to be my 2 dash. This would be my 3 dash. This would be my 4 dash. And this guy is my 1 dash. So what happens here? So let me write it. For a simple vapor compression refrigeration system, let's note down the values of H1 dash, which doesn't change. So that is 1430 kilojoule per kilogram. And H2 dash is what I'm supposed to find out. H3 dash is equal to H4 dash, and that is same as H7 and H8, which happens to be 380. So this guy is 380 kilojoule per kilogram. So let's just find out the value of H2 dash to complete this problem. So H2 dash, it's very closer to 1700, and it's exactly on the 1700 line. So let me say H2 dash is 1700. So 1700 kilojoule per kilogram. Now we are talking about a simple vapor compression refrigeration system without water intercoolers and intermediate compressor and high pressure compressor. All these are not there. Okay, so my refrigeration effect is going to be H1 dash minus H3 dash or H4 dash, however you want to call it, both are one and the same. 1430 minus 380. I think that is once again 1050. There is no change in the refrigeration effect. But let's look at the work input, which is going to be H2 dash minus H1 dash, 1700 minus 1430. So that's going to be 270, I believe. So let's cross check that. 1700 minus 1430. Yeah, it's 270. 270 kilojoule per kilogram. So what is the COP here? So that is 1050 divided by 270. 1050 divided by 270 is 3.89. So that is the COP. So when I use a simple vapor compression refrigeration system with no water intercooling, the COP decreases. So what is the percentage change in COP? So that is equal to 5 minus 3.89 divided by 3.89 multiplied by 100. So that would give you the percentage change. So let's look at that. So we would have 5 minus 3.89 divided by 3.89, which is 28.53%. So that is, so your COP decreases by 28.5% when you avoid using the water intercoolers. Okay, so that's all we have for this in this particular video. We will meet again in the next topic.